So hi everybody, thanks Dow Jones for having this really nice place, the Python Barcelona meetup, for having me here. So I'll be talking about three things today. It's a little bit of Pandas, a little bit of a project called Apache Arrow, and especially about PySpark and how it works. I wanted to speak more about Pandas and Arrow, and in the end, not a lot of people know how PySpark works, so I added that. It was too long, so I'll try to do everything, which may be a bit hard, but I hope you follow me. If I start speaking widely, please tell me to speak louder because I somehow have louder! Already? Come on!
Yeah.
Ah, shit. Yeah. So I'm Rubén. You can follow me on Twitter if you want. That's my handle. I'm a mathematician, not a data engineer, but I work as a data engineer. Things happen. I mostly use Python, Go, and Scala, usually, and I'm working at an advertising company in London. And yeah, we have all your data. Yeah, let's speak louder. Sorry.
Thank you.
So here, how many of you know what is Pandas? Nice.
The animal, right?
Yes. Of course.
It's a panda.
It's a data analysis library for Python, of course. It's used mostly everywhere, so if it's data and Python in a job offer, that's probably Pandas. If it's not, don't take the job, it's a bad idea. And it's really efficient, because it's columnar based, and the backend is written in C and Python, which is a kind of an extension of Python, which is kind of similar to C, and it's really fast. How many of you have read about this columnar thing in places and thought, what the hell does this mean? Because I've had. Okay. Smart people. I'm not, I looked it up. I probably knew it, but I forgot. So the thing is, imagine that you have a table with columns, some of them, and you want to sum a column. If you have your data spread across rows, when the CPU needs to access this, it's going to do it row by row. So we'll have a cache in the CPU which needs to access the memory. It needs to go to that element and get it, bring it down, and do the same for the next row. You will do it row by row because it can't access the column on one go. So when you're going to sum, it's going to be reading row by row, put it in the cache, get the data, and eventually it will sum. If you're working with a columnar representation of the data, you have just one column that you can access straight. The CPU is able to get that in one go, put it in the cache in one go, and sum straight. The difference is huge, especially if you are talking about big data, even if it's not big but it's in your computer. If you try to do it one way or the other with for loops, you can see the difference, and it's enormous. That's the point of the columnar thing that it's in Pandas and Postgres, well, Postgres not, Redshift and several others. And this brings me to the other thing that I wanted to mention today, which is Arrow. This is an Apache project, it's Apache Arrow actually, and it's a cross-language in-memory columnar format library. So it's supposed to be a representation of columnar data in memory library, so you can use it in Java, Python, C, and a few more, and there are bindings for other languages that I don't remember. The thing is that you can use the Arrow format to have columns in memory that you can access and process as columns quickly. You can do sums, aggregations, all that really efficiently. It's optimized for efficiency. The core is written in C. The Java parts are written in Java. The Python parts use Python and C. So it tries to be fast. And it's really seamless with Pandas because actually the creator of Pandas, Wes McKinney, wrote Arrow. So the ideas that he got from Pandas, he ported them to Arrow, and when he got Arrow working how he wanted, he kind of moved some information back, and now they are very, very much cross-compatible. So, Arrow loves Pandas, and Pandas loves Arrow. Internally, Arrow uses something called record batches. You can think of, you have a big table like I showed before, and a record batch, it's essentially a block of this table, and you have several, and that's your table. Pandas uses something called blocks, and it has a block manager. But you can think of it that it's essentially the same, but it's spread across columns. So you have kind of square pieces of columns, and you put them all together, and that's a table in Pandas. So you can convert a table in Arrow into a Pandas data frame really easily because the guy that wrote both made that happen. So it's like passing from one to the other, it's like instantaneous. In terms of speed, it's like one of the fastest things you can do in Python. And this gets me to what I want to talk today, which is about Spark, PySpark, and why Pandas and Arrow make PySpark after version 2.3 really, really fast. Okay, who knows what is Spark? Okay, and how many of you have used it, even if it's locally in your computer? Good. I hope you learned something today, maybe not. I hope. So Spark is a distributed computation framework. You have your data, you have many machines, you distribute your computation in several machines. Easy, more or less. It used to be really complicated. Then MapReduce happened, and Hadoop, and everything that came in between. And Spark made it a little bit easier. You don't need to think about what the machines do. You just write some code, and it may work or not. Usually it doesn't, but when it does, it's pretty much magic. It's open source, so if something doesn't work, you can go and fix it. It's not a complicated project to start working on. There are a lot of really small issues, and documentation is a little bit improvable. So you could help with documentation if you wanted. It's easy to use. I mean, when it fails, but everything fails. When it works really well. Good thing that it scales horizontally and vertically. So you can always go one larger machine, which usually is a bit cheaper in the cloud providers. So if you go for a larger memory and you try to pay less than market rate, it's better than several small machines. But you can go both ways. You can go larger machine with more memory, or many machines with little memory, and Spark will handle it seamlessly. If you can set up Spark in all the machines, it will work the same. So you write code once and it will work locally or remotely. So the first thing is, how does Spark actually work? Because it's a framework and it has machines and it has something and it magically works. The magic, it's a lot of smart people that have worked on this. But basically, you have Spark. It always depends on a cluster manager. The cluster manager is the system that knows how the cluster is distributed, how it works, and what it does essentially. Which machines are registered to the cluster, and all that. Usually the cluster manager is Yarn. I think it's Apache Yarn, but I'm not sure. It can be Mesos, which is a bit newer, but it's less used. And after 2.3, it can be Kubernetes, but that's still experimental. But it actually works. It's pretty cool. In addition to the cluster manager, you have the distributed storage. So you have some really huge files. They need to be somewhere. They actually will be here. Usually this is Hadoop or some version of Hadoop, like Amazon's S3. It's kind of a virtual Hadoop system. I think Azure and Google Cloud Compute Engine. Google has its own version of that. They are Hadoop compatible. That's the distributed storage. That's where your big data will be, and that's where the cluster manager will tell Spark where to get it. So when you have a Spark program, you write your code in something that's called the driver. So what you write, like load this and count the number of rows, that's code that you write and it's going to be executed in the driver. The driver is the one that is going to call the cluster manager and do everything for you. You don't need to know how the cluster manager works or how the distributed storage works. You just write read, count. That's it. That actually works because we have the Spark driver here, the cluster manager here, some nice machines here, and the Spark driver will have some tasks. Read, count. It will request some resources from the cluster manager. Hey, give me so many machines with this setup, which is going to be a Spark executor. Just here. It's how Spark workers are called. They are called executors. They are a Java virtual machine running whatever. And the task will be distributed across them. You don't need to know how this works. You write your code here, and all this comes from free. I think it's really nice because doing this is really hard. The machine does it for us. Nice. So how do you go from, okay, I have this execution model and I actually get something to execute? That's the idea that moved from MapReduce to a Spark, and why we have stopped writing a raw MapReduce and we moved to something else. That's the concept of the RDD, the Resilient Distributed Dataset. That's the main data structure that Spark uses internally. That's some data that it's resilient, so it's resistant to, if one machine goes down, you still know how to compute it. Supposedly, if everything goes down, everything goes down. But if one machine of 20 goes down, Spark can't recover from that because it's resilient. It's distributed, it's in several places. Usually it's more than one because otherwise it wouldn't work when one machine goes down. And okay, it has dataset. And how does a dataset look like? Here we have a happy dataset. So it has 5 items that make it a dataset. 3 are mandatory, so every RDD class, because this is going to be in the core of the Scala code inside of Spark. It's a class that's called RDD, and it has partitions. This is how you spread your data, like partition 1 is that file that is in the distributed storage, file number 1, file number 2 is another partition, or maybe not. It depends on how it's read, the system. It does it for you. There's a way of telling these partitions. Like this, we have from 1 to 100 some data. In addition to partitions, you can have, this one is optional, a set of preferred locations. So when you load some data, that's going to go into one of the machines of the cluster. Each partition will go somewhere. The preferred location for that partition from that point on, it's going to be there, because it's already there. Don't move it around. So in the beginning, this is kind of, it's optional, you don't need to have it. But eventually, as you start loading data, it's going to be there, it's going to be populated. There's also the most important part for me, it's the compute method. So every RDD has partitions, compute, something that I'll mention after this, but compute tells us we have this starting data and we want to do something, and we get something else. You can think of this as map. So map is going to apply some method inside of compute, and it will go from one partition to button. No. Okay. So it will map partitions from the top to partitions to the bottom. Think of doubling. So this will be the operation twice. It will go from partitions up, partitions down. It will have dependencies. To be able to recover an RDD if it goes down, what it does is that it knows on what it depends. Here we're going from these partitions to these partitions. So the output of this RDD are the partitions on the bottom. If for some reason this RDD disappears, meaning that this disappears, there's some notion of this partition was computed from this partition via this compute. And this partition is going to come from something here, which is the dependency, is what was there before. Eventually it goes to data that we read from a database or a distributed storage or something. So it's kind of from a fixed place, you can trace back the operations that made this possible. So if this disappears, you can still go back and start from the beginning and start recovering. That's the dependencies. Optionally, you can have a partition function to distribute these in a special way. If you know something about your data, like you have some postal code and you want to distribute per postal code, you can do that, but that's rarely used, but it can be handy sometimes. It's optional. But that was a Scala, because the Spark core is written in a Scala in the JVM, so it looks like Java a bit, but it's nicer than Java, like Scala, if you know me. But I also like Python. And how does PySpark work? Because that's Python, and the other one is a Scala. It's the one that does the operations. It's actually a Scala, it's not Python. How does this actually work? So PySpark is a Python API for the Scala system that is inside of Spark. So you write your Python code, like RDD read count. It will look like the Scala code essentially, but it's going to be Python, it's going to run, and it will work. To do that, it does some kind of a black magic, which is a library called Py4G, which is Python for Java, which is weird because for me it looks like Java for Python, but well. What it does is that it creates a connection from your Python code to the Java virtual machine. And with some black reflection magic on runtime, which is a bit ugly, it allows you to write calls to methods or to Java objects like it was Python. So you connect to the Java thingy, which is like this, and then you can import libraries like you will do in Java, like import package, and that's taken from the PySpark code. This is Python, even if it looks a bit weird. This creates a Java virtual connection, and this says to the Java virtual connection, hey, import me these libraries. So we have, how does this look in the code? This is a kind of a happy RDD in Python. In Python, we also have an RDD class, which is written in Python, but it exposes the methods from the Java one. So inside of every RDD in Python and most of the objects that are related to the Python PySpark code base, we have things that look like self underscore J something. And like M is for murder, sadly J is for Java. I don't like Java, happens. And this points to the object that exists in the Java virtual machine. So when you create an RDD in Python, this calls the JVM and says, hey, do this read for me. And when the JVM answers, Python via py4j is going to put kind of a pointer, if you want to think about that. It's just the ID of the object, but you can think of it as a pointer or an address to it. And then you can use it like if it was Python, kind of. It looks a bit ugly the first time, but since it actually works, it's pretty nice. So the entry points for doing this are actually RDD and PipelinedRDD, which is a subclass of RDD. This is in Python. So these are the entry points so you can create RDDs in Python or this stuff. If you want to have something that goes from Python to Java, these are the ones that you'll never use this one directly. This is for internal purposes, but I need to show how this works to explain how PySpark works. So when you create a Python RDD and you say compute on it, like you are doing a map, that's going to create a PipelinedRDD, which essentially grabs that one with the method. And that one will create a Python RDD in the Java virtual machine. It starts to look a bit like this animated GIF I put here, that there are a lot of kind of Russian dolls that are all together, and eventually something gets computed somewhere. And again, we have our sad RDD in Python land, and we want to map with some method. This is supposed to be an F in Python, so lambda x something. But in Python, that's the important part, that this F is in Python land. When we call RDD.map, that's going to create a PipelinedRDD, still in Python. It will put the F in a field called func internally, which holds the function, and it's going to point the previous field to that RDD. This previous field is for bookkeeping purposes. But this PipelinedRDD, it's a subclass of RDD, so it needs to have a JRDD. And this is the one that has the information about what to do with this, an F. It needs to compute eventually something from Java to Python. And that's where the Python RDD that I mentioned in the previous slide comes from. That's a class in Scala, which is another RDD, so it has dependencies. The dependency is going to point from previous to the JRDD. So this is kind of, from this side, it looks like Scala or Java to me, because dependencies point to something in the JVM. And compute is the one that is going to be a little bit weird, because it will hold something to be able to compute F of this. So it goes inside some kind of black magic, but I'll actually show how this works. Because the magic of this operation is what compute does to go from computing something that is Java objects with Python operations. So compute runs on every executor. So we have all our virtual machines running on different machines. We run compute, and then something happens and we go from Java to Python to Java again. This is done with a Python worker. I don't know why it's called worker, probably because it's worker.py. This is kind of a standalone process that is in Python. You don't need to write it. there for us, but it's going to take the f, evaluate it in each row of the JRDD, and return back. That's what Python runner does. So this is going back to the previous drawing. We had a Python RDD with compute. This is in Scala land or Java land, depending on how you see it. And we call compute on it, which depends on the function f. This creates a Python runner that has, again, the same name, func, that it's a wrapper for the function in Python. So as you may know, probably you have used the Pickle library, Pickle. You've used it probably, no? This is how you pass binary data from Python to Python. But there are libraries in Java to load that. That's what it does. When this function got into compute, it was pickled, it made it into Java as a binary, Java stores it, passes it to Python, and Python deserializes it. Easy. It's going to run it. So the worker is in Python, and the function is going to pass in a binary stream to the worker is going to evaluate on each row, going to send it back. Relatively easy. Internally it's a mess, but actually you can use, I think it's kind of 90% of Spark from Python without needing to worry about Scala or Java. The only problem is when something fails, because when something fails here, the error is Python. But sometimes what fails is either in the middle when the data is going from up to down, or it fails up. So what you get is essentially stack traces of JVM failures, which in Python look a bit weird. Also, the Py4j errors kind of get broken, so they don't look as nice as they would in Scala or Java. So it's like you get a bit of a Python error, Java error, more Python error. But if you don't do anything really weird, it usually works well. So I think I mentioned already everything that's on this slide. Workers are standalone processes. They have a main, actually. So Java is going to execute, it's going to fork the process, like Python worker.py, that has a main. This worker is going to connect back to the JVM, because as part of the parameters for the main, it has the port and the pipe. It's going to load and include libraries. So in the data that goes from Java to Python, it's like you need to be Python 2.7 or 3.6 or 3 point something. That information goes down. You need to load this library, this library, this library. If they are not available, it's going to fail horribly. Any broadcast variables, any information in the context is going to be serialized as well. So a lot of information is going from Java to Python and back. The worker deserializes the pickle function. It deserializes the number of rows, so it knows when it has finished. It deserializes also, I think, the kind of the data depending on the situation. It's a bit, I don't want to get into that because it may have some nightmares. Pass the function, returns the data. But there's something that I'm skipping here, especially for the ones that know about Spark already. That I'm talking about RDDs. And for the last 2 years, nobody uses RDDs. What we use are data frames, or in Scala datasets. A data frame, well, the thing is that data frames are easy to optimize, because RDDs, it's just data. There's no information about the data. You have rows. Rows of what? RDDs that doesn't know, doesn't care, and it can't care because of how it's designed. But data frames are different. You can think of a data frame like an RDD with information about columns. So it's not a row, it's a row of some things, and they have some kind of separation between the some things. Don't get into that, but that's how you can think of them, and internally they work like this. It's a pretty good abstraction of how they work. The good thing about data frames is that you have columns. So when you write queries to these columns, like count, select, where, that look like SQL, internally this is generating plans like your SQL database will create. You'll have query plans. This query plan will get optimized will get optimized, logically analyzed, I don't remember, there are like 5 steps until it eventually gets executed. So in the middle it's going to do a lot of things, so it can be optimized. The optimizer in PySpark, it's called Catalyst, Spark, not in PySpark. It's called Catalyst. You may have read about it because it was 1.5 years ago, a lot of blog posts about it. If you work only in Scala or Java, it does really fancy things because it's going to generate optimized code in Java for the operations. So in general, Scala is a really nice language, but it's not the fastest of the languages you can have in the JVM because of issues. And if you write pure Java like horribly, like you would do in C, if you've done C, like for loops and iterate item by item, it looks horrible, but it's usually more efficient than doing a map. That happens with Scala, that happens with Java. So Catalyst has a code generator part that can do kind of, it will generate code on the fly, it will compile it on the fly, and it will make your code really, really faster. The thing is that if you don't use user-defined functions in Python and you just do select, where, blah, count in Python, it's going to be as fast as Scala. Because nothing, only the eventual result is going to make it back into Python. Everything else is going to be still in the JVM, and eventually you get like 4 million. That's instantaneous. The problem starts when you start needing to serialize by defining user-defined functions, because there's no way for the Java magic to do any optimization on that. But after Python 2.3, there's something that can be done. Before, you could only define a Python UDF as a user-defined function for PySpark operations. So if you had a query like select 2 times this column, select expression 2 times this column, that needs to be defined as a lambda in Python. That's going to be an UDF in Python, and it's going to be run by this here, which is a subclass that Python runs. That is going to do essentially what I showed before, serialize and serialize constantly. But after Python 2.3, we have the Python Arrow runner that uses Arrow, and the fancy thing is that when it can use Arrow, it means that it can use Pandas. So this column operation, when it gets back to Python, it's going to be per column. It's not going to go row by row, it will go by column. The serialization is way faster, and the operation itself is way faster. So it's a win on 3 areas, and I'll show you here a bit why. This was the UDF runner. We have the worker. UDF runner is going to serialize a batch of rows. I think that's 100 rows, serialize everything in Python format, so everything will make sense to Python. It means that you are going from Java representation to Python, so this is a bit expensive. The worker is going to deserialize that. That's a pickle deserialization, which is quite expensive, especially in Python. It's optimized because pickle has been there forever, so it's not as bad as it could be, but it's pretty heavy. When it has deserialized, it applies the method f that went with the stream to each row, 100 rows, serialize again, and send them back. Because the only way from storing the data for Java is to have a binary format. So you need a pickle. So in the end, every time you are doing this cycle, which is every 100 rows, you serialize, deserialize, and serialize again. And repeat, and repeat, and repeat. With pickle, which is slow. Instead, you can use the Arrow, the UDFs in Pandas with the Arrow runner. What you send downstream is a Arrow record batch. But if you remember my 3rd or 4th slide, that's essentially like a Pandas data frame. So when you get back to the worker, you just say 2 Pandas. That's instantaneous because the internal format is essentially the same. So you have your record batch, you kind of move it a bit around, and then you have a table. You can actually run the function f to the column that you have just wiggled around. That's we could say that this is more or less as slow as this one. It's a bit faster, but not much. But the serializing and applying F a million times, well, 1 million times, but a lot faster than this. But the thing is that the other way, it was fast because when you had this Pandas data frame, you could convert that to a record batch just by moving it a bit around. So this is fast, this is not fast, but all the operations now in the worker are very, very fast. And that's what I wanted to get to today, which is that if you can use Pandas serial operations like sum, aggregate, there are a lot available now, and the kind of the newest work being done in PySpark is mostly focused on improving the Arrow availability and properties you can use. So there's a lot of growing, and 2.4 is going to be really, really much better. But if you can use Pandas series operations defined for the whole of the column, that can be from 3 times to 100 times faster than normal UDF definitions. So I mean, that's huge. I mean, this is more or less the speed that you can get from doing it directly in Scala, which if you've never done Scala, I don't recommend. Scala is really nice, but if you use Python, Python is really nice. And this is where I wanted to get. Some resources you can have a look if you want. Well, you could have with the Spark documentation. It would be really nice if you improve it. These 2 books are really, really good for how Spark works, like with really good details, but both are really, really Scala focused. There's nothing explaining how PySpark works or what to do with PySpark. There are a lot of small documents that you can have a look, but nothing up to date because it moves really fast. A lot of things have been improving lately. You can go to the GitHub of Spark and have a look, and I recommend you become a contributor. It's not terribly hard. The only problem is getting Spark to compile. It takes 1 hour and a half the first time. After that, it gets better and faster, but I really recommend helping with open source. And that's it. Any questions?
If you have any Python dependency that you need to install it like in all the workers.
When you submit the work, the job to the Spark cluster, you specify the dependencies, and then the driver will send that back to the worker. So installing, let me think about that. I think when you submit, it gets installed when the worker gets created. I'm not sure. I think it's part of the Spark submit command. So if you pass it there, libraries will be available, I think.
How do you see this against some new alternatives that are being created in the Python land, such as Dask, for example?
I really want to try Dask because so Dask is a distributed computing framework like Spark. Let me think a bit what I remember about Dask. It works a bit like Python, so it has this concept of it has a tree of operations and tries to optimize it. If you've played with TensorFlow also does that. It creates a tree of operations and tries to improve how they work. So in that sense, the 3 are similar. I think Dask has a lot of potential, and I actually want to play a bit with it because Spark is a bit slow sometimes. Depending on what you need to do, it's not the best solution. And I think Dask for harder, more kind of mathematical simulations, things that need more computing power, it may be a bit better because so Spark is for moving big data around but not doing much. And I think Dask is better for not so big data, but operate more on them. But I still need to play a bit with Dask before I can combine. But I think it's a really cool project. I think Wes McKinney, the Arrow guy, is working on bringing Arrow to Dask, but I think it's still work in progress.
Thanks for the great talk, Rubén. So, a few years ago, there used to be a belief or opinion that with PySpark you could achieve only very basic operations, and I know they've done a lot of work and so on, and they always said that if you really want to get a lot from Spark, you need to use Java, and from what you said, the things have changed. So, does it happen to you sometimes that you can't achieve something with PySpark and you have to switch to Scala?
Well, the thing is that at work, 2 years and something ago, our big Spark project was about to start, and we thought we can achieve anything with PySpark, so we moved to Scala. So I've been doing only Scala Spark since then. Everything I do in PySpark is for my own fun, contributing code, because I know enough Scala and enough Python to help on both sides. From what I've seen, you can do essentially everything. The thing is that usually the APIs in Scala are always a bit better, because work is first done in Scala and then it's done on PySpark. And some things in PySpark are a bit harder because of all this serialization. It's not as, the Python virtual machine is a bit worse than the Java virtual machine, because Java virtual machine, well, I think it's newer, but it has gone through a lot of iterations, a lot of improvements, so it can handle large memory much better. But I think if we had to decide now on that project, I think I would have gone for PySpark, because Python is usually nicer to write with. For data exploration, PySpark is much better than using the Spark shell with Scala. In Scala, eventually you need to define the type of all your columns. I like type safety, but it's a pain in the ass when you are just getting some JSON and want to see a few rows. I think right now PySpark is pretty much as useful as normal Spark. Okay, thank you.